In the last presentation, we completed 3-bit asynchronous up counter. Now I want a 4-bit asynchronous up counter. So let's see what changes we have to make to get a 4-bit asynchronous up counter. Again, the flip-flops are asynchronized. The clock is not given simultaneously to all these 4 flip-flops. You can see QA, the output of the A flip-flop, is given as the clock to the B flip-flop. Similarly, QB is given as the clock to C flip-flop, and finally QC, the output of the C flip-flop, is acting as the clock for the D flip-flop. So they are asynchronous counter, and definitely they are up counter because we are considering QA, QB, QC and QD as the output. Therefore they are up counters. You will see in down counters we consider QA complement, QB complement, QC complement and QD complement. Then it will count in the reverse manner and we call it the down counters. We will discuss it later. But now you have to see one more change is the type of the flip-flop used. I have used T flip-flops in this case, whereas in the last presentation I used JK flip-flop. There is no problem using T flip-flop because we just require toggling, and T stands for toggling. So why to use JK? We can directly use T flip-flop and we can give the logic 1 to all the inputs TA, TB, TC and TD. You can see they are connected to a logic 1, and in that case we have toggling. So this is one change, and definitely the number of flip-flop is changed. Instead of having 3 flip-flops, I have 4 flip-flops because I have to make a 4-bit asynchronous up counter. This bit is the output of the flip-flop. So if I want to increase the bit to 4, I have to use the 4 flip-flop instead of 3. So these are the basic things that I want to tell you at the beginning of this presentation, and you know how to analyze this, how to get the output waveform, and we will do it quickly. Then we will see the truth table for the 4-bit asynchronous up counter. Before that, let me tell you one more thing. I have already told you how to get the state of the counter. It is 2 to the power n, where n is nothing but the number of flip-flops used. So I have 4 flip-flops, so 2 to the power 4 is equal to 16. So we have 16 states. This is states. So we have 16 states in case of 4-bit up counter, and we can also find out the maximum count, and the maximum count is given as 2 to the power n minus 1, that is 16 minus 1, which equals to 15. So it can count maximum 15, and 15 is nothing but 1 1 1 1. So this is the output of the flip-flops, and this is the maximum count, and the minimum count is definitely 0 0 0 and 0. So we have to count from 0 to 15. So this is our task. Let's see how the waveform looks for this arrangement. I have made the clock, and the clock is the external clock that we are giving to the A flip-flop, and as the logic 1 is given to TA, definitely we have toggling, and we have to find out QA. So let's find out QA first. Initially QA is 0 and it will remain 0 for the first falling edge. You can also see the flip-flops are negative edge triggered, so we have to consider the falling edges for the change, and we have toggling. So QA will be complemented and it will remain high for the next falling edge. In the same way, it will be complemented and again remain low for the next falling edge, and then again the complement of 0 is 1 and again 0. In the same way, we have to complete till the 16 clock pulses. I will not complete for the 16 clock pulses because I know you can do it. I will just do it for, let's say, 9 clock pulses. Okay, and this QA is now given as the clock to the B flip-flop, and we are interested in calculating QB now. So I have QA as my clock, and I will consider all the falling edges, and QB is my output. Again TA is equal to 1, so we have toggling. It is low initially and it will remain low for the first falling edge. Again it will go high and remain high for the next falling edge, and the toggling will take place. The toggling is very important concept. You can see the whole counter is dependent on it. That's why I took 2 or 3 presentations to explain you what is toggling. So this is my QB. Now we can have QC, and for QC, this QB is acting as the clock, and we will consider the falling edges. These are the falling edges. Initially it is low and it will remain low till the first falling edge, and again it will go high for the next falling edge, then it will go low. Now the interesting part comes, and actually the change come if you compare it with the last presentation. We have the another flip-flop, so another output D, and now QC is the clock, so we have to consider the falling edge. This is the falling edge, and for this falling edge we will get the toggling, and the toggling will make 0 1. So this is how the timing diagram of a 4-bit asynchronous up counter looks. Now we can have our truth table, and we will complete it very quickly because there is nothing new in the truth table. We have the clock and we have the outputs, and before writing the outputs, let me tell you, QA is my LSB, the least significant bit, and QD is my MSB, the most significant bit. So I have QD, QC, QB, and then QA as the output bits. And you can also write the decimal equivalent in the next column. We will find out these bits before the first falling edge arrives, and I will call that duration initial duration, and we will see from this timing diagram what are the values of QA, QB, QC, and QD. This is my first falling edge, and before that you can see QA is 0, QB is also 0, QC is 0, and QD is 0. So all the 4 bits are 0. So I will write 0 0 0 and 0, and this is definitely 0 in decimal. The first falling edge, and then the second falling edge, then we will directly see the 9th falling edge, and the falling edge between the 2 and 9 you can definitely find by yourself. So we will check for first, second, and 9th. Let's see for the first what we got. QA is 1, QB is 0, QC is 0, and QD is 0. We will see for the falling edge number 2, QA is 0, QB is 1, QC is 0, and QD is 0 also. And we will see for the 9th falling edge, in this case QA is 1, QB is 0, QC is 0, and QD is 1. So you have to remember these things: 1 0 0 0, 0 1 0 0, and 1 0 0 1. These are the values of my output bits for the first, second, and 9th falling edges. So let me write it down. For first I was having 0 0 0 1, for second 0 0 1 0, and for 9th 1 0 0 1. Let's try to find out the equivalent values in decimal number. This is 1, this is 2, and this is 9. In the same way, if we calculate for the 14th falling edge and the 15th falling edge, let's see what we got. For the 14th falling edge we will have 1 1 1 and 0, and for the 15th falling edge we will have all the bits high. So this is the equivalent of 14. 8 plus 4 plus 2, this is definitely 14, and this is 15. So you can see we are counting from 0 to 15, that I have already told you 15 is the maximum count, and in total we are having 16 states. So this is all you need to know about 4-bit asynchronous up counter. This is a up count starting from 0 and ending at 15. We are having the higher values with increasing clock pulses. So this is all for this presentation. In the next presentation we will see the state diagram of the clock, and then we can move to the down counters. So see you in the next presentation.